All right, question 53. Not a bad problem for this late in the test. Generally, I'm not a huge fan of linear algebra, but I found this problem to be pretty intuitive and one that you can do pretty quickly. So the key to this problem is understanding the dot product. Informally, all the dot product is just a measure of the extent to which the direction of two vectors agree. What I'm saying is if you have two vectors and they're pointing in kind of the same direction, you're going to have a positive dot product. If they're pointing the exact same direction, you'll be maximizing your dot product. If they're pointing in opposite directions, you're going to have a maximal negative dot product. If they're perpendicular, your dot product's going to be equal to 0. If the angle between two vectors is acute, right, or obtuse, the dot product is positive, 0, or negative. And that's all you need to answer this question. I'm not trying to make you an expert on this question. I'm trying to make you understand dot products and the concepts of this question well enough so that you'll be able to answer a similar question on the test correctly. So I'm going to talk a little bit more about dot products before I actually answer the question. But for this specific question, this is plenty. A more formal definition of dot products conveniently encapsulates this informal idea. So say we have these two vectors u and v, and we want to find the dot product between these two vectors. We can draw these two vectors in standard position. I guess I might as well take advantage of some color here, and consider a third vector, the projection of v onto u. Turns out dot products are commutative, so you could also consider the projection of u onto v and end up with the exact same answer. But for my picture, I'm going to consider the projection of v, this vector in red, onto u. That would create this vector in blue, maybe I'll call it w. All the dot product of u and v is the magnitude of u, how long this vector is, times the magnitude of w, how long this vector is. This assumes that when we project v onto u, u and w are pointing in the same direction, but it's entirely possible that we had some other v, maybe I'll call this v1, that when we project it down onto u, would point in the opposite direction of u. Maybe I'll call this w1. If you're in this case, you just got to throw a negative out in front to encapsulate that idea that w and u are going in opposite directions. That's it. Note that the magnitude of u and the magnitude of w are automatically positive numbers, so when we multiply them together, we automatically get a positive number. So the dot product will always be positive unless we're tacking on that extra negative. Another way to think about that is that if the angle between u and v is acute, then when you project v down to u, w and u will end up pointing in the same direction. If they're pointing in the same direction, the dot product is going to be positive. That's this first statement right here. If instead the angle between u and v is obtuse, then when we project v down to u, w ends up pointing in the opposite direction. We get a negative dot product. And finally, if the angle between these two vectors is a right angle, maybe I'll call this v2, then when we project v down to u, the vector w that we create is just the 0 vector. And the length of the 0 vector is 0, and 0 times anything is 0, so the dot product is going to be equal to 0. That's this middle statement here. A cool consequence of all of this is a formula that ends up being really useful. In fact, it's a statement that I've already used on this test, way back here in question 37. It's that the cosine of the angle between two vectors is always equal to the dot product of those vectors divided by the product of their magnitudes. If you multiply both sides of this equation by the product of the magnitudes, you get that u dot v is equal to the product of the magnitudes times the cosine of theta, where theta is the angle in between the two vectors. And again, since the magnitudes are always positive, u dot v will be positive if the cosine of theta is positive, which for angles between 0 and 180 degrees happens only if theta is acute. It'll be negative if the cosine of theta is negative, which again on the interval in question happens only if theta is obtuse. And since the cosine of 90 degrees is equal to 0, the dot product will be equal to 0 if the two vectors are perpendicular. You don't need to prove statements like this, but anyone who's taken a pre-calculus 2 class could do so. It really just comes down to this picture right here and the old mnemonic SOHCAHTOA, which tells you that the cosine of this angle theta is equal to the side length adjacent to this angle, so the magnitude of w in this case, divided by the hypotenuse, or the magnitude of v. The dot product is just the magnitude of u times the magnitude of w, but from this equation we see that the magnitude of w is just the magnitude of v times the cosine of theta. Sure, I'll write it down, why not? So if we plug in for the magnitude of w up here, we get that u dot v is equal to the magnitude of u times, instead of the magnitude of w, we write the magnitude of v times the cosine of theta. The dot product of u and v is equal to the product of the magnitudes of u and v times the cosine of theta, which if you divide both sides of the equation by the product of the magnitudes of u and v, gives you this handy little equation right here. All right, that's more than enough on the dot product of u and v. We could have answered this question a long time ago. What the question tells us is we have these 4 vectors in R2, and we're considering 6 different dot products. The first question is, could all 6 of these dot products be negative? Absolutely not. Why? Well, because the only way the dot product between two vectors is negative is if the angle between them is obtuse. And the 6 dot products that we're considering are all the pairwise combinations of these 4 vectors. So draw your first vector, put it wherever the hell you want. Maybe I'll throw it on the x-axis. It really does not matter. Here's my first vector, v1. I'm trying to make all 6 of these dot products negative, so when I draw v2, I better make sure that the angle between v1 and v2 is obtuse. What that means is that v2 better either be in the second quadrant or the third quadrant. Without loss of generality, I'll throw it up here in the second quadrant. Here's v2. So far, so good. Now we consider v3. We need the angle between v1 and v3 to be obtuse, but we also need the angle between v2 and v3 to be obtuse. Is that possible? Well, sure. If we pick the right angle down here in the third quadrant, we could certainly make that happen. But when we get to v4, we get in trouble. The angle between v1 and v4, v2 and v4, and v3 and v4 has to be obtuse. That's not possible. Maybe you can see that just from this picture, or maybe you can prove it more by contradiction. Suppose it was possible. Suppose you drew the 4 vectors that made it possible. Suppose you labeled those vectors A, B, C, and D, starting on the positive x-axis and naming them counterclockwise. So we have vector A here, and then more than 90 degrees counterclockwise of A is vector B, and then more than 90 degrees clockwise of vector B is vector C, and then more than 90 degrees clockwise of vector C is vector D. But now there's a problem. A has to be more than 90 degrees counterclockwise of vector D, but when you add up these 4 numbers, each of which are greater than 90 degrees, you get a total greater than 360 degrees. You see that this is not possible. Okay, could I have 2 of them be negative and 4 of them equal to 0? Well, let's see. I know that if the dot products are equal to 0, the vectors are perpendicular, right? The angle between them is a right angle. So one way I can make the dot product between v1 and v2 be equal to 0 is by putting v1 on the positive x-axis and v2 on the positive y-axis. If I decide to throw v3 on the negative x-axis, then the dot product between v1 and v2 would be 0. The dot product between v2 and v3 would be 0. And the dot product between v1 and v3 would be negative because the angle between them is obtuse, 180 degrees. I think that's obtuse. What I need to do is add one more vector that gives me 2 more dot products that are equal to 0 and 1 more dot product that's negative. Can you think of how to do so? What if we threw v4 on the negative y-axis? v1 and v4 and v3 and v4 are clearly perpendicular, so their dot product is 0, but the angle between v2 and v4 is 180 degrees, therefore the dot product is negative. Adding that to our little list over here, we see that we have 4 pairs of vectors that have a 0 dot product and 2 pairs of vectors that have a negative dot product. We've satisfied the criteria for statement 2. Unfortunately, 2 only and 2 and 3 only are both options, so we have to look at statement 3 here. Statement 3 is a lot like statement 2. We still want 4 dot products to be equal to 0, but now, instead of the other 2 dot products being negative, we want the other 2 dot products to be positive. Well, since this answer is so much like this answer, maybe we can draw a picture that's very similar to this picture. We still want the dot products of 4 pairs to be 0, but now we don't want any negative dot products, so we can't have vectors pointing in opposite directions. So what if we just flipped v4 and v3? Put v4 up on the positive y-axis, put v3 over on the positive x-axis. All right, something like this. Switching colors is kind of a pain, so maybe I won't color code this one. But let's see, the dot product between v1 and v2 and v1 and v4 would both be 0. And the dot product between v3 and v2 and v3 and v4 would also be 0. Oh, we don't want the others to be negative. We want them to be positive. Sure, I can pretend I didn't mess that up. v1 and v3, the angle between them is 0. 0 is acute, I think. But whatever, they point in the same direction, so their dot product is positive. Similarly, v2 and v4 point in the same direction, so their dot product is positive. This picture would satisfy this criteria, so we see that statement 3 certainly could be true. Looks like the answer to the question is D, 2 and 3 only. One thing that I'm just realizing is that as I solve this, I never used the 0 vector anywhere. I wouldn't be surprised if we could recreate situation 2 and situation 3, allowing one of the vectors to be the 0 vector. Let's see, maybe we can just talk through it. If v1 is the 0 vector, the dot product of the 0 vector and any vector is going to be equal to 0, because the magnitude of the 0 vector is 0. So v1, v2, v1, v3, and v1, v4 would all be equal to 0. So then statements 2 and statements 3 can kind of be rewritten by just considering 3 vectors, maybe v2, v3, and v4, and asking ourselves the question, is there a way to write them so that 2 of the dot products are negative and 1 of them is equal to 0? Well, yeah, that doesn't seem too hard. Maybe down here. I need 1 dot product to be 0, so we'll start with 2 perpendicular vectors. Now I've got my 4 0 dot products, so I just need to create 2 negative dot products. Negative dot products happen when the angles between the vectors are obtuse, so just throw v4 somewhere down here. v2.v4 is going to be negative, v3.v4 is going to be negative, and as I already talked about, the dot product between v2 and v3 is going to be 0. We get our 4th 0 dot product and 2 negative dot products. Same thing for statement 3, letting v1 be the 0 vector again. and throwing v2 and v3 on the positive x and y axes respectively. This gives us 3 zero dot products. Here's our fourth zero dot product. We need 2 positive dot products, so just draw v4 so that the angles between v2 and v4 and v3 and v4 are both acute. That gives us the 4 zero dot products and the 2 positive dot products that we're looking for in case 3. Obviously, you don't need to solve these problems multiple ways. I just want to make the point that sometimes considering the zero vector can reduce the problem into something that's easier to conceptualize. But whatever picture makes more sense to you is great.